Hello, good morning, good afternoon, everybody. Welcome to today's Lunch and Learn. My name's Kristen Gastaldo. For those of you I haven't seen before, I'm the Director of Self-Service and Community for IFS. So I manage the IFS community, and I hope I have seen most of you guys in that space at some point in time. For those of you who haven't attended a Lunch and Learn before, these are part of our success sessions. These sessions cover our Tech Talk Lives, office hours, Lunch and Learns. This is designed to be a shorter session, so about 30 minutes. Thank you. Thank you. They're designed to be about 30 minutes, so you get to see a demo or a presentation, and then you have time to ask some questions. We do these about once a month. We're having a little bit of a lull in the summer, but they're going to kick back up in the fall, and they'll be happening at least every month for you. Today, we're joined by Bob De Caux, who is our VP of Automation. He'll be covering artificial intelligence, particular to IFS Cloud PSO. So we'll talk about what that looks like now and how it might change and drive the future for field service at IFS. If you have questions, please feel free to drop them in the chat or drop them in the questions section. I'll hold them till the end, and then we'll have Q&A when the presentation's over. So Bob, hand it off to you.
Thanks, Kristen. So yeah, as Kristen says, my name's Bob. I run the automation group, and what that basically means is, well, there's two main streams really. There's the artificial intelligence, and there's the optimization, so solving large-scale optimization problems. And the developers within my teams manage both of those. And today we're going to talk a bit about how those two worlds, those two streams, if you like, come together, how AI applies in the optimization space. So I'm going to start by talking a little bit about what AI is, because there's obviously a lot of misconceptions. There's a lot of keywords and buzzwords that get used and sometimes misused. So I'll talk a little bit about what AI and machine learning is, and some other techniques which relate more to the types of problems we solve. Then I'll talk about specifically what we're doing with AI within the IFS Cloud PSO product at the moment. And then we'll talk about the journey to predictive service, so how we can actually start planning things in advance of the optimization problems based on what you know is going to happen in the future. And finally, we'll expand that even further to talk about outcome-based service contracts, so how we can connect up assets, get them to feed information into the mix for maintenance, how we can help our technicians in the field with knowledge and other similar areas. All right, so I'll begin with the AI overview. So if you saw the talk a few weeks ago from Karan, Jason, and Justin, who are my colleagues in the automation team, they started with a similar slide. AI is really the big umbrella, and that is basically the different studies of how we can use computer algorithms to learn and solve problems, often in a human way, but with a bit more of a focus on rational behavior, because sometimes humans don't always make the best decisions. The aim is for AI to try and do so. And the subfield of AI that's probably most well known is machine learning. That's really where we learn, or where computer algorithms learn patterns from often large sets of historical data. Now, AI and ML are often used interchangeably, but ML is a subset of AI. And deep learning, which you've probably also heard about, is a subset again of machine learning. And the idea with deep learning is you're stacking a lot of these models together to try and create more interesting behavior, in the same way that the human body will have a model of the eye, and the eye will behave in a certain way, and that will feed into the brain and into the whole body and determines how we see and interpret things overall. But as well as these areas, there's a few other areas within AI that are a little bit different. Natural language processing is how we analyze and synthesize natural language and speech. So this is a big growth area in terms of being able to understand what people are saying, be able to understand what people are writing, be able to pull out the important keywords, the important sentiments from that, and turn that into actions. Then you've got expert systems. These have been around a lot longer, and that's trying to really codify the way humans make decisions in terms of if-then type rules. If these criteria apply, then I will do this action. And you can create huge systems based around this. But the other area is one that probably doesn't get talked about as much, is evolutionary computing. And this is where we're taking inspiration from techniques in nature, particularly related to sort of Darwinian evolution. And we're turning them into algorithms that can help us solve optimization problems, because the idea with evolution is that over time, we are evolving as a population in terms of our attributes and what we do and what our skills are. And the same principles apply here. So you can take a problem and you can evolve a set of possible solutions. So over time, they get better at doing something, which will hopefully give you a better answer to what you're trying to achieve. So evolutionary computing, what are some of the techniques within that, some of these inspirations from nature? Well, one is genetic algorithms. This is the idea where you do have this population of possible solutions, and they're made up of genes in the same way that humans are. And each of those genes will characterize a certain type of behavior that that individual will have. And the idea is that you test an individual against a particular type of problem. It may do well, it may do badly. And if you have thousands or millions of those individuals, you can see which ones are doing particularly well, and you can push them through to the next generation and then hopefully evolve a population based on those ones. And the idea is that you're taking the characteristics that make a solution do particularly well through from generation to generation, and you're hopefully getting better at the problem you're trying to solve. Ant colony optimization, this is a technique based around how ants leave messages for each other. Effectively, they leave behind a chemical trail called pheromones if they think there's information that they want to pass on to other ants within their colony. And that might be, you should follow my path, this is where food is, or it might be, don't follow this path, you know, there is danger. And over time, with this very simple behavior, as enough ants are doing this on scale, you evolve a sort of path through a system, through a network, again, to find the best possible solution, which for an ant will often be, you know, finding food. But for us, when we're trying to use it to solve a problem, it might be the optimal route through a set of jobs, for example. And the third technique is the idea of simulated annealing. This is something we use a lot within the platform, and it's based around the concept of how a metal cools once it's been heating. The idea is that the atoms within the metal are sort of vibrating and settling down to a certain state. And as they lose heat over time, that parameter controls sort of how far those atoms are going to move and sort of explore possible coordinations that they could settle down into. And it's the same concept when we're looking for a problem. You know, we use the idea that we start with the solution being very hot. So we will explore you know, a whole map to try lots of different routes, for example, for where technicians may go to try and shorten their path between different cities, or to make sure they can do their jobs as quickly as possible. And over time, we will cool that algorithm so that we're not exploring as far afield anymore. We're just focusing on smaller areas, like within this postcode, you know, how should a technician move between these particular streets in order to, you know, travel most efficiently between their jobs. So that idea of moving from a very general solution to something that's a lot more localized, a lot more specific, is really a core part of the algorithms that we have within our PSO software. And I'll talk a little bit more about what PSO is in a minute. Just briefly to sort of highlight what AI means to us at IFS, and this is driven by the differentiators we had within IFS Cloud generally, and it's probably focused on these three you can see on the left. Innovation being embedded. So the idea is that when we do AI, we don't want to provide toolkits for data scientists or technical specialists to have to work to solve their own problems. We want the business users to be able to solve those problems out of the box, for all that technical complexity to be hidden away. And that applies equally in the sort of scheduling and optimization phase. One single product means we've got one data source. So we're not trying to integrate lots of products together. We always have the data that's going to allow us to do the learnings that we need to make better decisions. And industry depth. We're not starting with the technology. We're always starting with the use case we're trying to solve. So often within the scheduling problem, we're starting with field service. We've got real world jobs that technicians need to do. We've got a number of technicians who can go and do those jobs. And there's, you know, various attributes about those jobs, skills, parts, service level agreements that we have to meet. So it's very important that we're always thinking about the real world problem we want to solve rather than the technology we need. All right, so how does this work within PSO? So as probably a lot of you know, PSO is our planning, scheduling and optimization product. And what it's really doing is solving a problem called the traveling salesman and doing it at scale. And the idea of the traveling salesman problem is, you know, I've got a number of jobs that I need to do. Well, in the original problem, it's a number of cities I need to visit. What's the best way I can visit those cities so I can minimize my travel time? Now, of course, when we're doing this in the real world, we're not just looking at cities or jobs that we have to do. We have to factor in all manner of other things. We have to factor in skills, the proficiencies of the technicians, SLAs, where the jobs are linked in some way. But even without all those prerequisites, the combinations available here for the different routes that technicians can travel are absolutely vast. You know, we can see it's jumping from, if you've got 2 possible technician resources, 4 work orders, you've got 120 possible paths. By the time you're at 5 resources and 30 work orders, you know, that number is absolutely enormous. So the key point here is we're trying to solve a problem that we're never going to get a perfect solution to, because we're never going to know if that's the best possible. So we're always trying to do as well as we possibly can. So that's the idea, really. When is our solution good enough? And you're always trying to trade off the quality of your solution in terms of, you know, minimizing the distance our technicians have traveled, for example, against how long it takes to come up with that solution. And that's where we really specialize. We're very good at taking incredibly large problems, coming up with a very good solution quickly that is going to be good enough in the vast majority of cases. So how do we use AI in all this? Well, I like to think of it in sort of 3 ways throughout the process: solve, adapt, and learn. So solving, we have an optimization problem to solve here. We have all these technicians who can go and do a variety of jobs. You know, how do we set about finding what the best way for them to do those jobs is? And so what we use is a range of optimization techniques. Some of those are very simple, things like a greedy algorithm, where we just go to the, you know, the highest priority job first, for example, and then take the next highest priority one. That will give you what we call a starter solution that does a reasonable job, but is probably not optimal. And so the AI, in fact, helps us in the background to choose which of the techniques we should be using in order to get the best possible solution for our scheduling problem. And we have a number of possible techniques we can use there, around 30, and it will find the combination of those that works best. And those techniques work in different ways, as we'll see in a minute. So that's the initial solving, but a crucial part is adapting, being able to adapt your schedule as things change throughout the day. If technicians are sick or if new jobs come in, you've got to do these things dynamically. So running things in batch at the start of the day means probably your schedule is going to get out of date very quickly. So the idea is that we want to keep re-optimizing solutions as there's changes throughout the day, but we don't want to have to keep restarting and optimizing the whole problem again. So the key thing that we do for our dynamic scheduling is start with our good solution and sort of change it, perturb it slightly, move a little bit away from it to try and find the best solution based on the changes we've seen. And AI can help us again with how we do that. And finally, learn. This is where we can take experience from the past, from, you know, how jobs have been performed, how technicians have traveled between different jobs at different types of day, and we can use machine learning to make better predictions about what that's going to mean in the future. For example, you know, if technicians are traveling early in the morning during rush hour, it's going to take them longer on certain routes than at other times of the day. So we can learn a whole host of things that can help us actually feed into the optimization problem and allow us to solve it better. So let's look at that solve part in more detail. So I mentioned there's this hierarchy of different algorithms that we could use. So we tend to begin with this starter algorithm I mentioned, something greedy, where we're just taking the most important jobs first. And then what we'll do is we'll split it into a population of possible solutions. And this is where the genetic algorithms come in that I mentioned earlier. So each of those possible solutions will have a set of characteristics, and we'll evolve those characteristics over time to see if they can get better at solving the high level problem of where all our technicians should be. But the key is often that problem is huge. We have thousands of technicians, hundreds of thousands of jobs. So we have to find a way to break that down. And that's where AI can come in and help us with the clustering. It can break down often the jobs in geographical location or in time into different problems that can effectively be solved independently or in a connected way, which makes it easier to do. If you're solving a ginormous problem of hundreds of thousands of jobs all at the same time, it's going to take absolutely ages and you might not even be able to do it. If you can break that down intelligently, it allows you to solve that much faster, and that's what the AI helps us to do. But then at the level below that, once you've broken it down, you still need to do this local search, where within these smaller areas, within a county, within, you know, certain postcode regions, you know, what's my best routing at a street level, for example. And that's where local search algorithms come in. They're really optimizing against, you know, these very fine-grained characteristics. And that's where we use simulated annealing, that metal cooling technique, which is sort of trying to sort of test small different routes that are similar to what they have now, but slightly different. That's kind of our main workhorse algorithm, if you like, within our PSO product. So this hierarchy work together. They work together in different ways. Some of them have different weightings at different times. And all of those weightings are controlled by artificial intelligence in the background. And the idea here is that as a human, therefore, you don't need to get involved. You know, it's taking the effort out of solving this problem away from the human and into the hands of the computer. And that's very important because all problems are slightly and subtly different. And there may be certain restrictions about linked activities or clusters or geographical regions, which are better, left handled automatically by the computer algorithms than with human intervention. And that's the way we set things up. So if we talk about adapt in a little more detail here, I mentioned this idea that over time, the quality of your scheduling algorithm will degrade as things change throughout the day based on the real world events in the top right hand corner, text calling in sick, appointments being cancelled. So what do we do, or how does AI help us there? Well, what happens is we always have the existing schedule in mind, and then we have this concept of change types. And these are changes that we can apply to the solution to see how they will affect the schedule. Will they make it better in some way? And those changes may be to add a technician, to flip the order of jobs. There's a vast range of possible change types that we can have there. And the idea is in the background, we've got various heuristics and AI controlling how important those different change types are. So it might be that flipping jobs is really effective, or moving the jobs from one person to another is really effective at this point in time, given perhaps we've lost a resource. And what this does is it allows us to tackle the entire scheduling problem at once, and that's really important. What we don't want to be doing is sort of cycling through different geographical regions, for example, optimizing each of those individually, and then cycling round, and by the time we get back, we find that that is now out of date because something has changed, new jobs have come in, and that schedule doesn't work anymore. By tackling the whole problem at once, by breaking it down efficiently, by applying these heuristics, as I mentioned, so that we can take a solution and not have to start again each time, we can just subtly change it. That allows us to be much more efficient and keep that schedule working really well. And that increases the automation. It allows us to improve our SLA hit rate, means we can minimize the travel for the technicians on the jobs. So the learning I mentioned, this is using historical data to make better decisions in future by using machine learning algorithms. And a good example of that we have in the product now is our automated intelligent travel profiles. This is where we're working with our partner TomTom on trillions of historical GPS points to understand driving patterns at different points of the day, different days of the week, in different types of weather. And what we're able to do is we're able to incorporate that information, all those learnings historically, into our travel matrix, which is used for calculating the travel between different points on a map. And so, depending at what time your technician is moving, or what time, or when during the week, or in what type of weather, it's automatically going to adjust those travel times based on the best prediction of what it's going to be. And that obviously feeds into the optimization more effectively and should give you a better idea of how long your techs are going to take to travel, and hopefully, ultimately give you a better schedule. And there are other ideas of learning that we can talk about, particularly around sort of being able to predict how long jobs are going to take, for example. So this isn't all theoretical. The importance is that AI is actually driving practical benefits. It allows us to solve bigger problems. That's really important. And we were able to solve a problem with 500,000 jobs that we were able to provide a very good quality solution for, with a 99% sort of SLA hit rate within an hour. And that's a bigger job than we'd ever find really out in the field. But we wanted to show that that solution could scale, and actually allowed us to win innovation awards last year, particularly the UK National Innovation Awards, where we finished runner-up. But this actually has a knock-on effect to your business. It's going to improve your dispatch to tech ratio. It's going to increase your productivity with big numbers. As we can see on the right, these are real numbers that our customers are deriving from this technology, and it's all driven by the AI-based approach. So this isn't just theory. If we were to strip this out, we wouldn't be able to solve these large problems. We wouldn't be able to get anywhere near these types of benefits. So the journey to predictive service, we've talked about optimizing jobs that we have already. What if we were able to understand more about what jobs we're going to have in the future, or the types of jobs they were going to be? And so this is the idea of how AI can help us along that path. So a very easy sort of first step is the travel duration I mentioned, being able to predict how long journeys are going to take based on those various factors, such as the weather, the time of day. The next one along, probably in terms of complexity, is being able to predict how long jobs are going to take. This will be based on, historical precedent for the type of job it is, parts availability, skills availability, location. Those sorts of things can feed in and give us a more accurate estimate of job time, which will ultimately give us a better schedule. So that learning is fairly, straightforward. We've done the first one, and the second one is going into the products, in forthcoming release. And then we move on to predictive scheduling. This idea of, can I know in advance what jobs I'm going to have based on the weather? If it's particularly stormy, is that going to affect or knock out my assets and mean that I'm going to have to send technicians round? Are there events going on which means that my technicians are going to have to reroute, or there's likely to be a certain type of job in a city centre at a certain time? So again, we can use machine learning to predict what those jobs are going to be and to feed them into our optimization as if they were real jobs. And that gives us a more accurate sort of distribution of our technicians, a more accurate schedule to work around. And then really what we want to be able to do is think, well, how could these things change over time in different circumstances? So this is the idea of adaptive scheduling. If I want to set myself targets and business goals, how can I adapt the SLA characteristics and conditions automatically to be able to meet those goals? What does it mean in terms of the number of technicians that I need to have in order to meet these goals? And the idea is that the engine will be able to take these goals in and work out exactly how many resources you need, what they need to be doing, the parts, etc., in order to meet those goals. And so the final instantiation of this, we've talked about the activities side, thinking about the resources themselves. Actually, given that we know how many activities or the types of activities we're going to be doing, what does that mean for our resourcing? Does that mean we don't need so many people on at a different time of day? We can automatically work out our resource requirements and feed that into the equation. And so this is the route that we are working on our roadmap. Some of that's already there, as I mentioned, the first one, second one well on the way, and those next three are coming in over the next sort of 12 to 24 months into the products, those increasing complexity. And that really gives us that forward-looking view to combine with this optimization technology. We now have this view of what is going to happen to the business in the future. And we do already have our What If Scenario Explorer, or WISE, which allows us to test some of these hypotheses. Now, if I was to add more resources, what would that mean for my schedule? If I had changes in demand, what would that mean for my schedule? And what's actually happening in the background here is, again, using intelligence. It's using AI. So given a certain number of resources you have, what the engine in the background will do is take that resource and try lots of different optimizations, and it will try to find out what the best balance of technicians would be to meet those jobs, for example. And it does that intelligently. Obviously, you've got a huge range of possible technician values you could have and different skills. What it will do is it will use certain heuristics, it will use machine learning to find out, where the sweet spots are, which is going to have the best effect on your schedule. So again, that forward-looking view is something we already have to some extent through the WISE, and that again is taking advantage of intelligence in the background. So if we then sort of broaden things slightly further from just the scheduling and optimization part to think about outcome-based service contracts, what are the tools we need to be able to deliver those in field service generally? So one of those is obviously the ability to optimize our resources. That's the one that we talked about, but there are really three others that we can offer within IFS Cloud, or we will be offering within IFS Cloud. One is automated decision making. So, based on certain conditions at a certain point in time, do we need a human to actually say yes, no on whether a work order is needed, for example, or can using machine learning that decision be made automatically? We'll look at an example of that in a minute. Technician assistance. So can we help technicians more in the field by bringing them back more pertinent knowledge quickly to help them do their job, to help them understand from what they can see in front of them how to do something more effectively? Or could we populate the tickets, the work orders more effectively so that it's easier for the technician to do their job when they get there? And IoT and predictive maintenance, this is the idea of, certainly if we're dealing with assets in the field, can we connect up those assets, have them feeding information in, saying how they're doing right now, and make predictions about what we think that's going to mean for their future performance? You know, is the temperature of those assets going up? Are there increased vibrations? Are there a combination of things that mean we think there might be a job needed at some point in the near future, and so I should raise a work order for that to get a technician out there? So these are the types of tools that can all feed and complement that optimization and scheduling we talked about earlier to complete that field service experience, and they all rely on AI to some extent. So that predictive maintenance I mentioned, for example, what is actually happening there? Well, when we're doing it within IFS Cloud, what we're doing is we're taking in a whole host of readings from sensors on the asset. We can combine that with data on the asset history, and we can use it to make predictions about what that asset's going to do in the future. And this was something, again, that Karan, Justin, and Jason covered in their talk a few weeks ago, talking about time series data. And this is the idea that if we look over time at what something's doing, we're able to, using AI, extrapolate that forward and understand if we're likely to see any anomalous behavior. Is temperature going to fall outside this boundary or something like that? And it's those types of anomalies are the things that will drive the work orders. So if we're making these predictions and we flag some kind of alarm or some sort of alert that we think there's anomalous behavior coming in the future, then we'd raise a work order off the back of that to get a technician out there. But it's not just about, you know, under maintaining your assets. It could also be over maintaining your assets. You know, if actually everything is fine with the asset, we probably don't need to get a technician out on their calendar-based maintenance. They're going out every month. Maybe they don't need to go this month because everything is fine. So what you're trying to do is increase the asset uptime, but ultimately you're going to get the value from utilizing your technicians better. And that's how it ties in with the optimization and scheduling. Automated decision making. So one example would be, based on the type of job and all the information we've gathered, is that job going to be something that a technician can fix first time? And we'll factor in the availability of the site, the skills needed, spare parts. And then what we can do is we can build what's called a supervised learning model using machine learning. And the supervised learning model is simply saying, well, what I'm trying to predict against is whether this job is A or B. And in this case, A or B is just, I'm going to fix it first time, or I'm not going to fix it first time. And we know certain types of jobs are going to go into category A, certain types of jobs are going to go into category B. So what we're able to do is insert that model into the workflow. So when we get a new job in, we can run it through, and we can get a probability back from the model of whether it thinks it's going to, whether it thinks the technician is going to be able to fix it first time, or it's going to require multiple visits. And the benefits is obviously we can plan for problems in advance. But we've seen when we've been working on this with one of our customers as a proof of concept, we've actually seen it can incentivize the technicians as well to, you know, beat the model. You know, often the model will say that it thinks it's going to require multiple visits. That actually can incentivize the technicians to try and do it in one visit to, you know, prove that it can get one up on the AI, which is quite an interesting behavior we've seen. It's the sort of, you know, hidden benefit, if you like, from using this type of approach. And finally, technician assistance. I mentioned this idea of an intelligent knowledge base. What we really want to do here is to take all the learnings that you as a company have in the past, that be all the notes technicians have taken, all the manuals you've got, images, pictures of assets, etc., and combine it all into something that's easily referenceable and easily questionable by a technician. So what we do first of all is what we call cracking, where we take all that information, all the historical documents, and we turn that into the key pieces of information, what we call the entities, that are going to actually drive a decision. So, you know, what the key parts of an asset are, for example, which are most likely to fail. And then we put all that information into what we call a knowledge graph. So this shows how all these different pieces of information are connected. And then the idea is that we use then natural language processing, something I mentioned at the start. So this idea that we can take a question as a human would say it, we can interpret the meaning, the semantics, and the different types of things they're asking, and we can turn that into a question that we can ask of the graph, and then we can bring back the relevant information. So for example, a technician may be at a certain point in their journey in terms of a fix, they want to know what to do next, Effectively, we can take that current state, we can take all the information they have and come back with the next best action. So this is something that we are putting into the product over the next 12 to 24 months. We have the first use case for this at the back end of next year. And the idea is it provides that advice to the technicians out in the field. It can also provide that advice earlier in the process. You know, when we're populating that work order, what is it that the technicians will need to know in the future to allow them to do their job more effectively? All right, that's where I'm going to leave it. So, you know, we've covered what AI is, how we're using it at the moment within our planning, scheduling and optimization, how that is going to expand to think about being able to predict jobs and sort of forecast demand in the future, and then more broadly, how AI can help in other ways within that field service experience. So at this stage, I'll hand back to you, Christian, and see if we've got any questions.
Awesome. Thank you for the presentation, Bob. That was great. It's like a ton of content, right, to get through in 30 minutes. There we do have a couple questions. So any plans for predictive parts functionality?
Yes, it's an area that, you know, we know is done by others in the market, and it's certainly something that has easy potential from a machine learning point of view to do. So yes, that is something we are definitely looking to bring in at some point in the future into the product. Yes.
Okay, thank you. Let me see one more. Do we have the competitor intelligence for how this stacks up against our field service competitors who offer AI in scheduling and optimization?
Yes,
like
to, you know,
question.
Yeah, to, you know, to, yeah, I mean, yeah, it comes down to really a question of scale. I think, you know, I think we're able to work at a much larger scale due to the way we take very large problems and decompose them using AI. You know, there will be overlap in techniques that are used to some extent, but the combination of those techniques, how we do that from a proprietary point of view, and how we can break down those particularly large problems and especially solve them all at once, so that, you know, as the problem's changing over time, we can stay on top of it. That's what really differentiates us.
Those are the two that have come in so far. This session was recorded, everybody, so we'll be posting it in the community. So if you wanted to share with any colleagues that weren't able to attend today, you're able to do that. And if you have follow-up questions, you're welcome to post those in the community as well, and I can get those to Bob. There's a section for field service with FSM and PSO, all in that same section. So feel free to post any questions in there. And I guess that's it for today. Then thank you all for attending. I'll put the webinar up probably later today in the community, so you'll have access to it before the weekend. And again, thank you, Bob, for presenting.
No, so thank you very much, Christian. Bye-bye, everyone.